Hello, we are Team 3 Uganda Forever presenting our results and process with producing a vaccine for Uganda. Our presentation will include an introduction to the task followed by two different subtasks, probe and heating and mixing. It will come to an end with a conclusion and our references that we used to do our research. Our task is to create a bioreactor to immunize Uganda against tuberculosis. Based on our research, herd immunity is achieved when 85 till 95% of the population is vaccinated. We decided to vaccinate the whole country as the increasing cost between vaccinating 95% and 100% is comparatively low. We've researched and collected the information we're going to need to produce a vaccine that is going to be effective in helping in lowering the number of infected people. Factors taken into consideration include the design parameters, calculating the cost, and the scale-up considerations. Ethics. It's been vital to keep the community of Uganda in mind as they are the center of this whole project. We considered their response in this new vaccine and ways in which we can form a healthy relationship. For sustainability, the distribution of net gain should be centered around self-sustaining and long-term improvement in living standards of the population. For cultural context, we've researched the issues that can arise due to cultural differences and suggested ways to mitigate them. Risk and security. The way to mitigate environmental risk is by disposing liquid hazardous waste in an underground injection well. We haven't changed any parameters after the test and build phase. For the electrode placement, during the initial tests that we ran, the height of the solution was at 8 blocks. The electrode placement was not something that we could test, so we had to work with assumptions based on mentor advice and base our choices off what we read on the internet and our individual interpretation. The assumption that we worked with was that the input probe's placement didn't matter and that as long as it was connected to the bioreactor. We chose to place our gold and iron probes opposite to each other at a height of 4 blocks. The reason is because we assumed the signal would run across the largest amount of solution possible, such that it would be representative of the total volume being tested. The input was placed perpendicular at a height of 3 blocks. We placed it so that it would be out of the way. Lastly, the ground went perpendicular and below to the gold and iron probes at a height of 3 blocks so that it doesn't interfere with the signal but could pick up excess charges as it's meant to do. For the gain settings, the reason for our choice is that this setting gives a reading with the least noise when tested. It also doesn't amplify the voltage too much, giving very high VPP levels with negligible increases.
During the testing phase, we have conducted the following calculation using the constant resistor value provided in the information sheets associated with the project. As 8 volts is the voltage that gives the highest current, we decided to use 8 volts for our input. We came to a conclusion that 8 volts is ideal as it gives the lowest impedance since the relation between impedance and current is inversely proportional. Also, we were hoping that if every cell acts as a resistor in series in the direction of the current, there will be more voltage input per cell, which would give us a stronger signal that would be easier to read. Surrounding the cell's conducting core is the non-conducting plasma membrane. Thus, a cell suspension can be regarded as a suspension of spherical capacitors surrounded by a conducting suspension medium. When an electric field is applied, the ions in that solution are forced to move. The positively charged ions are pushed in the direction of the field, whilst the negatively charged ones are pushed in the opposite direction. The ions both inside and outside the cell can only move so far before they encounter the plasma membrane, which acts as an insulating physical barrier, preventing further movement. This results in the development of charge separation. At very high frequencies like 10 MHz, few ions have the time to polarize the membranes, resulting in negligible membrane polarizations, giving a negligible contribution to the overall capacitance. We weren't able to test the values, as such we chose 400 kHz. We thought it's better to use a frequency value as low as possible, however we decided against using frequencies lower than 100 kHz, as in the real world, metal electrodes attract a counter layer of ions around themselves, which acts as a large capacitance in series with the suspension, which we suspect manifests as a large increase in amplitude in the testing frequency ranges. On the web, found the following impedance frequency graphs for the PBS and yeast solutions, which hint at the results we can expect. We've also assumed that since impedance equals V over I, the amplitude and the impedance are directly proportional, so these graphs can show similar results to what we'd expect from an amplitude frequency plot. If we remove outliers at the 3 to 6 hour mark, we see a general increase in the voltage as the concentration of the solution increases. However, the graph does not follow the trend that we would expect. We suspect this is because we had to use lower frequencies to make the concentration changes have a larger impact on the output. What we did not account for is that the simulation would not have been a 100% accurate representation of the real world. As such, we conclude that the use of electrical impedance spectroscopy is a viable method for testing, and our results suggest that it is best to do it in a frequency range below 100 kHz. The yeast concentration against time graph shows an exponential growth, as expected from our research. The concentration of yeast kept rising until the 15th hour, peaking at the concentration of 47 grams per liter. A slight plateau in the graph can be seen between 15th and 16th hours, and this is known as the stationary phase. After the 16th hour, the yeast concentration started to decrease as the population of these reaches its peak and starts to decline. We've included a calibration curve of the amplitude and yeast, which follows the expected trend of increasing amplitude with increasing concentration. During the 24-hour run phase, we were able to adjust the gain to give a clear sine wave to compensate for our inability to test beforehand, and we've changed the gain to 1 and 10 for channels 1 and 2 respectively. There were other options that gave us a sine wave, such as 1 in 100, 1 in 1000, and 10 in 1000, which didn't match our expectations as it was too amplified.
Selected optimum condition to maximum protein synthesis in order to obtain the maximum yeast concentration for our bioreactor. Reduces overall production costs and allows us for scalability. Different environments due to inefficient circulation of waste product can lead to cell death and trigger transcriptional induction of alternative cell genes. By microenvironment, we refer to temperature gradient, toxic waste gradient, areas of depleted oxygen, or uneven distribution of feed. Overall, an even distribution of feed and nutrients was to be prioritized in the design because temperature in fermentative processes should not deviate by more than 1 degree Celsius. The graph on this slide shows the effect of speed on mixing time for different impeller layout. The general trend is that as the speed increases, the mixing time decreases for most combination. From the graph, we can see that the impeller layout that gave the lowest mixing time were combination 8 and combination 9. To choose the best impeller layout between combination 8 and 9, we plotted a graph of mixing time against power to see which combination delivers similar performance while consuming less power. Therefore, for our final design, we chose to pick combination 9 as our impeller layout. We also plotted a graph of mixing time against power for all the different impeller configuration with different agitation speed. The reason the mixing time decreases as power consumption increases is because higher agitation speed allows mixing to happen quicker, which translates to more power being consumed. From our experiment, the lowest mixing time achieved was 4.89 seconds, but that used 25,000 watts of power. Therefore, we decided to pick combination 9 as our final impeller layout, which produced a mixing time of 12.52 seconds and a power consumption of only 1800 watts. As reference, comparing our bioreactor to a standard microwave, which also uses 1800 watts of power.
The choice of impeller is a double stereo combination with a 4-pitch blade impeller placed at the top and a standard Russian at the bottom. The configuration successfully generates large-scale asynchronous circulation loops of the vessel walls, both downwards and upwards, resulting in aeration throughout the bioreactor. A radial Russian impeller is essential for efficient heat transfer as it produces large turbulences towards where the vertical baffles are located. Having it placed at the bottom breaks up the 4 downward trailing vortices produced by the upper pitch blade impeller. The standard Russian is a high-speed impeller with minimum energetic consumption, which when combined with the pitch blade would ensure an ideal compromise between low mixing time and a high cost associated with increased power output, thus reducing operational cost. The Russian is the most commonly used in baffled fermentation vessels in yeast culture industry. These type of high-speed impellers can be used for this type of strain of bacteria in vaccine production, as the robust cell wall of the yeast is able to withstand any potential shear force. As seen from the graph, using the baffle conditions produces a lower mixing time overall. With this in mind, we decided to choose 4 uniformly spaced hygienic baffles. Baffles reduce tangential component of velocity and effective heat transfer coefficient, thus reducing the chances of vortex forming, increasing fluid velocity, reducing mixing time, and creating a better heat distribution. However, having more than 4 exponentially increases the energy consumption due to lower pumping efficiency. Our chosen agitation speed was 120 RPM. It allows efficient heat transfer and increases the surface area of the culture that is in contact with the media, hence achieving greater cell density. Lower RPM would not have resulted in sufficient bubble breakup necessary for the oxygenation of yeast. It was found to produce homogeneous mixing without hindering cell growth due to high shear forces. As seen from the results we obtained, increasing the RPM decreases the mixing time but increases the power consumption significantly.
We decided to make the water level our control variable through the initial test of the parameters. This allowed us to see the effects of the impeller combinations and the mixing speed. After choosing the combination that compromised between a good mixing time and power usage, we then tested this combination with different water levels. As seen in the graph, the lower the water level, the faster the mixing time, which was the result we expected to see, as the volume being mixed would be lower. Therefore, we decided to use 6 blocks of water, which would be 3/4 of the height. This allows the aerobic restoration of cells and mixing at the top of the liquid, as it is not too far away from the impeller zone. The optimal growth for yeast is between 30 to 37 degrees Celsius. Outside the optimal temperature range, the ability to catalyze the reaction slows down or the enzyme begins to denature. Therefore, we decided to have the temperature set point of our bioreactor to 34 degrees Celsius, as it is an approximate midpoint. The metabolic activity of the cells will create unwanted heat in the bioreactor. This increases the temperature in the bioreactor, thus hindering cell growth. Mixing can also increase the heat. There is also a possibility of losing heat to surroundings through the walls of the bioreactor. In order to overcome these difficulties, we decided to use an external jacket. This will ensure tight temperature control in the bioreactor, making sure that heat is being transferred in and out. This is a better alternative to the use of internal structures for heat transfers because internal structures can interfere with the mixing inside the bioreactor, and a broken piece of the internal structure can contaminate the solution or even cause permanent damage to the bioreactor. After plotting a mixing time against speed graph for the theoretical and experimental results of our chosen combination, we found that our experimental mixing time results were lower, which means we can produce the yeast concentration quicker and also have a lower power consumption. The electrode from the probe is internally placed at the bottom of the reactor. This may interfere with the radial circulation routes generated by the bottom Russian impeller, which reduces bulk mixing by opposing the mass transfer of media. Consequently, effective mixing is reduced and the time taken for the fermentation of yeast cells may increase. Our chosen parameters gave us the yeast concentration very close to our assumption. Despite the trend on the MVPP against time graph, our yeast concentration value was not far off our assumption, indicating that the probe does not affect the mixing in this case.
To summarize, only our bioreactor capacity and the capacity per batch is changing due to the almost similar result of the yeast concentration. Everything from estimated and power consumption is roughly the same. Our working hours during the manufacturing of vaccine is 8 hours a day, from Monday to Friday, and also we will shut down the bioreactor for 3 months for maintenance.
After calculating our operating and facility costs, we can see that our total cost of project is approximately 120 million euros.
Use the World Health Organization fund, and also this project would be financially viable as Ugandan government is committed to subsidize medical advancement and promoted improved living standards.
Increasing reactor size decreases surface area to volume ratio, leading to diabetic microenvironment and to fermentative metabolism, which we want to avoid. A solution would be to add a submerged aeration unit which ensures sufficient oxygen supply. The size of the turbine as a percentage of the reactor diameter increases, which significantly increases power consumption. We would recommend trying different configurations, such as having 4 equally single spaced impeller steerer shaft, a hollow steerer shaft that allows oxygen delivery underneath the turbine, or impellers with holes to decrease cost of propelling longer blades. Furthermore, there is an inverse relationship between mixing time and power consumption, so we must account for the considerable trade-off, and therefore it is ideal that we chose to use a double configuration with a high-speed Russian impeller and a lowest speed consuming pitch turbine at the top. Bioreactors used in fermentative processes do not conform to the standard tank diameter liquid height ratio of 1:1. Aerobic culture's common ratio is more like 3:1, as the vessel needs to be tall enough to allow for rising dissolved oxygen bubbles enough contact time with the yeast cells, and allow higher hydrostatic pressure at the top, helping improve gas-phase oxygen transfer. As such, when scaling up to tall vessels, it is best to use multiple impellers mounted centrally. Although separation distance should be greater than our initial 1 diameter so that the different circulation loops do not oppose one another. For uneven temperature gradients upon scaling up, we can implement external heater exchanges. However, residence time in the external unit must be kept to a minimum to avoid any potential loss of oxygen from the medium. For large fermentation bioreactor, cooling jackets are unsuitable as they do not provide enough heating area. Internal heaters units lead to large temperature gradients, reduce mixing time, complicating sterilization and cleaning, and lead to film growth producing blockages.
Our estimated yeast concentration is 50 gram per liter. However, after the 24 hours run, we obtained 47 gram per liter for the yeast concentration. Now, our new value of bioreactor capacity per batch is 24,469 liter per batch. Changing of bioreactor capacity will affect the overall cost. Now, our cost per dose is slightly higher than the initial assumption by 7 cents, which is 1.29 euros, which doesn't really affect much of the overall cost. Therefore, we can conclude that we got a good yeast cell growth at the end of the 24 hours run. We do need to consider other non-technical factor possibilities that might affect our cost per dose if we would do it in real life, such as the tariff, any tax or import cost that we need to bear since we are importing this vaccine to the people in Uganda. In conclusion, we get a good yeast cell growth from the 24 hours run result due to our final yeast concentration is almost similar from our assumption. This is affected by our bioreactor design selection for mixing and also with the ideal frequency and gain settings that gives us an ideal mixing time for the growth of yeast. From the 24 hours run result, we have a cost and yeast concentration which is almost similar from our initial assumption. And this is the reference that we use for the resources and also the reference we use for the image.